Hello, so in this video, in the final part of differentiation, we're going to look at modelling, right? So we're going to look at real life problems and real life questions to do with differentiation. And you'll see a very key component of these questions will be to do with minimum and maximum points, right? Which we looked at with stationary points, where the minimum and the maximum can give me some idea about perhaps the lowest or the highest value of something, okay? And that leads into the idea of optimization, okay? So optimization optimization gives us the best possible, or even worst really, or the worst possible outcome of something. So, for example, optimization could be, optimize a company's profits, or they want to minimize losses, or they want to minimize the time taken. For example, if you want to drive or move from one point to another, what's the least time you can do it in? So there's a ton of applications where we want to optimize to find the maximum or the minimum of something, and this is where this will come into play, this idea of maximization and minimization of the maximum and the minimum points, right? Okay, let's then go back to basics a little bit. And actually, if I then write down my derivative dy dx, that means, as a recap, it means changing y over changing x. Right, it's basically to do with gradients, right? So dy dx, you can think of it as like a line. When we looked at first principles at the start of the chapter, we used this idea about gradients, right? How the derivative gives me the gradient, which is changing y and changing x. What that means is then we can think of it as gradient, but also we could say it's the rate of change. So then I can say that dy dx tells us how y changes when x changes, okay? So for example, so you can think of it as a straight line, right? So as an example, if a straight line had the equation, let's say y is 4x minus 3, well, the gradient is 4, right? M is 4. That means when x changes by 1, y changes by 4, okay? That's what that means, right? So this whole derivative, dy dx, you can think of it as a rate of change. It's how y changes when x changes, okay, with this idea here. And that's really the idea we're going to look at, right? And again, we can then look at real life scenarios where one variable affects another variable. So one variable changes, how does the other variable change? Okay, so let's go over a sort of simple example to give a sort of analogy for what's going on, right? So, for example, we can consider a paddling pool, right? A swimming pool like this one, right? And we can sort of we can model it. It's reminiscent of a sort of cylinder, right? A cylinder, right? So if I draw a cylinder which kind of sort of represents this pool as so, if I can draw it right, okay, let me draw it a bit better. Okay, I'll take it. Okay, there we are. So a paddling pool was something like this, like a cylinder shape, right? So it has a base, and then obviously the water fills up to a height of h, and then it's at the end there, right? So the idea is, obviously, we fill water into my paddling pool, and then at the end the shape expands, right? So originally a swimming pool is just flat, right? And it doesn't really have much shape to it, right? it's kind of limp. But then as we fill up the water, fill the tank, fill the pool up with water, the shape expands, right, and it becomes more like a proper circle, right? It fills up, so it rises, right? The paddling pool rises, and it starts to form a proper shape, right? And so the idea is the shape can change. This cylinder can change shape and move about as we add more water and we change the height of it, right? So this leads us to the idea of considering how things change, right? So we know in general that the volume of a cylinder, the volume V, is pi r squared h, the radius, right? The radius here, and then the height h. Right. Let's say the h obviously is the depth of water, right? So obviously we're going to add water into my paddling pool. Very horrible drawing of one, of a cylinder, but there we are. So if you imagine we are adding water into my pool, into my cylindrical pool, paddling pool, until it rises and reaches the top, right? So the height changes, right? So I add in water and it changes, right? So my height changes. So my volume changes, right? Because volume depends on h, as you can see in the formula here. So what we can sort of investigate is how the volume changes when the height does, or the depth of the water, so how high up we are in, right? So what we can then consider is the derivative dV dH, and that will be change in volume divided by change in height, right? Because that's what a derivative is. Okay, so dV dH, change in volume over change in height. Okay, so how does the volume change when height does? Well, actually, this is a derivative, right? dV dH. We also have an expression for V in terms of H here. We can then differentiate, right? We can differentiate the volume formula V and differentiate the H. So if we treat everything else as basically a number, a constant, right? So pi r squared, imagine it's just a number k, right? How would you then differentiate H, right? Again, if you can even imagine H as x, right? But how would you differentiate H, right? It would just be k, right? Because remember, k is pi r squared. So dV dH would just be then the number k, the number in front of H. That'd be pi r squared, right? So that tells me actually the expression for that when the volume, the change in the volume, when the height changes in my paddling pool, is equivalent to pi r squared, the radius at that point, right? So, okay, let's say the radius is 5. Let's say r is 5. Then dV dH is going to be well, 25 pi, right? So what that tells me then, that 25 pi, that is a rate, right? That is tells me that when the height changes, the volume changes by 25 pi, or increases by 25 pi. Okay, so for example, if the height changes by 1 centimeter, then the volume changes by 25 pi centimeters cubed. Okay, so that's the idea, right? Again, it's a sort of gradient, right, at the end of the day. So we can find the change in one variable, say the volume, with respect to another variable, say the height. So in this case, how we interpret this, dV dH, when the height changes by 1, the volume changes by 25 pi. It's again very reminiscent to when, say for example, if we had the line y is 4x minus 3, the gradient is 4, which means as x changes by 1, y changes by 4. That's the whole idea of a gradient. It tells me when one thing changes by how one variable changes, how much does the other variable change as a result. Okay, that's what this whole thing is telling me. Okay, and this is the idea of rate of change. So this differentiation tells me ultimately, if one thing changes, then how much does the other thing change? And that's what it is. Okay, and that's what we'll be looking at in this section. Okay, how real life quantities and how real life variables such as volume and height and so forth, how does one thing change affect another? Okay, and so yeah, so we're going to look at some examples to illustrate this now. So we are told that a volume V of an expanding sphere is related to its radius r by the formula V is 4/3 pi r cubed. Find the rate of change. So when you see rate of change anywhere in a question, that's going to be differentiate. Okay, as we just discussed, rate of change, how one thing changes when another thing changes, that's all to do with differentiation. That is your dy dx or whatever, right? So very, very important tip here: if you see rate of change, that language, it means differentiate. So find the rate of change of the volume with respect to radius at the instant where the radius is 5. Okay, so we got the volume then, and then it's told us to find the rate of change, which means we're going to need to differentiate this expression, right, with respect to radius. So that's saying, how does the volume change when the radius changes, right, in simple words. So we need to differentiate, but we need to differentiate the r variable. Okay, so if you think of it as r as x, then it's kind of like 4/3 pi x cubed. But then how you differentiate that if it's just x, right? That would go to, well, the 3, the power, as we know, the power comes to the front. So it'd be 4/3 times 3 pi x, and then we knock 1 off the power. That'd be x squared, right? So then 4/3 times 3 is just 4 pi x squared. Well, actually, that's my differential, but x is r, so it'd be 4 pi r squared. Okay, so that's it, right? That is my rate of change, or the volume with respect to radius, or in other words, the derivative of the volume when we differentiate the radius. Okay, right. So that's my derivative then, right? Because now it told me to find the change when the radius is 5. Well, that's what we're going to do. We're going to substitute r is 5 into here. So then dv dr is going to be 4 pi of 5 squared. If I put that in the calculator, I get 100 pi. Okay, and that's it. So that will be in, well, what would the units be? Now think about it. It wouldn't be centimeters cubed. It's not volume per se. It's the volume when the radius changes. So it'd be centimeters cubed over centimeters, right? So that'd be centimeters squared. And yes, and if it helps, to visualize what the units would be, think about it. dv dr, well, v is centimeters cubed. That's my volume unit, right? And then I'm practically dividing by the radius, right? You can think of it like that. So then the radius part is centimeters, right? So because I'm dealing with volume over radius, I'm doing the units, right? Centimeters cubed over centimeters. That goes to centimeters squared. Hence my unit here. So all I'm doing is dividing the volume unit by the radius unit to get my unit of centimeters squared for my rate there. Okay, and that's it. So then that tells me that overall, I guess if I were to interpret it, I don't have to write this, but I guess to help, that tells me the volume is changing by 100 pi centimeters squared when the radius is 5 centimeters, right? Centimeters. So let's say, for example, every minute or every hour or something, or every second, right? When the radius is 5 centimeters, then every second, let's say, I don't know what the time is, but the volume will then be increasing by 100 pi. Okay. Okay, but obviously then if the radius is changing, then obviously the volume will change as well. But at that moment of time, at that instant moment of time, when the radius happens to be 5, because the radius will be changing, it won't be 5. Again, think about the pool analogy at the start, because obviously originally with no water, if you imagine a water pool, it'd be completely limp. It'd be quite disformed, like the shape. But then when you put more water in, it starts to rise up and expand. So the shape changes. So the radius would change. Okay. All the radius would change. So it won't be 5 centimeters all the way through, because it's talking about an expanding sphere. If a sphere is rising, the radius will have to change as well. So all that's saying is at the absolute instant, the moment when it reaches 5, then that's the rate that the volume's changing. Okay, but yeah. Right, okay. Okay, let's have a look at this question then. We're told a large tank in the shape of a cuboid is to be made by 54 meters squared of a sheet metal. The tank has a horizontal base with no top. The height of the tank is x meters. Two opposite vertical faces are squares. Show that the volume is this expression here. Right. A lot of stuff going on here. It's probably good to have some sort of sketch maybe to visualise what's going on. So it's a cuboid, right? So it's going to look like this. If again I can draw it somewhat decently. Okay. There we are. Okay, something vaguely like that, right? So at either end, it's going to have this face here, and then obviously it has that face at either end, and then obviously has this top and bottom, and then the side here. So it has all these faces on in this cuboid here. Okay, so what's it saying then? So that's my cuboid. We're told it's to be made by 54 meters squared of metal. That's the surface area, okay? That's a good hint that it's a surface area, because the units are meters squared. Remember, anything squared is an area, okay? Meters cubed is a volume, right? And meters on its own is a length or measurement. And that's the same if we wanted to move it to kilometers, or if we moved it to centimeters, anything like that. That's my sort of units, right? So because it's meters squared, it's the area of all my 2D faces, okay? So I need to find that out, okay? And that's from GCSE, finding surface areas of shapes like cuboids. So my surface area is 54, right? I'm then told it has a horizontal base, which you can't see, but hopefully you can visualise. It's going to be the opposite. It's going to be underneath the top shape I've dashed right there, and it has no top. Okay, that means basically the top is open, right? It's not filled in with anything, it's just open, right? So things can go in directly from the top there, okay? The height of the tank is x, so the height would be like this. That's x then. And the two opposite vertical faces, that's this, right? It's this shape, and if you can imagine the shape on the other side, right, that would be facing that way. Anyway, so that shape there, that vertical face are squares, Okay, well actually if that's a square, then this shape of here, if that's x, then that also has to be x. All the sides are the same in a square. Right, so that leaves me with this measurement here, right, how far along it is, right, which is y, right. I'll call that y. I don't know what it is, so I'll just call it y. Okay, now it's talking about finding the volume, right? So let's go about just trying to find what the volume will be. And with a cuboid, you should be familiar with that the volume will be the cross section or the area of this face here, which is x times x, which should be x squared, times by this sort of length there, y. Okay, of how far wide it is. So the area of the cross section and how far wide it is. Okay, so x squared y, x times y. So that's my volume. But my problem is, if you look at my volume expression here, it only has x in it. I have a y. I need to find what this y is, right? This is where this surface area is going to come in, and I'm going to need to work that out as well, right? So I'm going to work. So the surface area then, overall, all the faces, right, necessary, all the faces have to add up to 54. Okay, so let's work it out. Let's work out one at a time. So the surface area then of this cuboid, well, we know it equals 54, but in terms of, you know, x and y. Let's try and work it out using the shape, right? So firstly, you got this shape again, this square face, and there's going to be two lots of these, right? Because you can imagine it's forward and it's one at the front here, and there's also going to be one at the end, which obviously, hopefully, you can visualize is at the back end, right? There, it'd be facing that direction. So it's going to be two lots of these with x and x. Then we also have these side faces. So again, there's going to be one at the front here and one at the back there, right? It's going to be two of those as well. So we need the area of that, and that's going to be y down here, and this length is going to be x as well, right? So x here. Then we have the top and the bottom, right? Lastly, but you would think then it'd be 2 times the top and the bottom. We know again the length here, it's going to be a rectangle, right? So it's going to be y, and then that length is going to be x, so it's going to be yx. But it wouldn't be 2 of them, would they? Because we need to look at the question. Obviously the top and the bottom, right? So imagine the top face and then the floor, right, of the shape, right? Again, you can't really see, but hopefully you can visualize the top and the bottom of the roof and the ground, right? If you think of it like that. But it wouldn't be both the top and the bottom, because it told me the tank has no top. So that means the top here, as we said, it's open. There's no area to cover it, right? So we do not include that in my surface area. Okay, so it'd just be one lots of it at the bottom. Okay, just one lots of this rectangle. Okay, so then if we just compute the area of these individual 2D shapes, the square and the rectangles, well, 2 times the area of this square, and that's 2 times x squared, right? Then we can have 2 times this rectangle, that's going to be xy. Then we're going to have 1 lots of this rectangle, xy as well. So then we can just collect like terms. So we're going to get 2x squared, 2xy and xy would be 3xy, right? And that's it then. So that's my surface area, but I'm told the surface area is 54. Right, so I can equate that to 54. Now the idea is, again, remember my volume has a y in it. I don't want a y in it. So it's kind of like simultaneous equations with this equation here and this equation here. So I need to get rid of y. So I'm going to rearrange for y, right? So I can then say, if I want y on its own, then 3xy is going to be 54, take away 2x squared. Then y is going to be 54, take away 2x squared over 3x. And there we are. And so then I can split up the fraction to simplify. So then I can say that y is going to be 54, well, 54 over 3 is 18, so it's going to be 18 over x. Take away, by the way, what I'm doing, I'll write it down more carefully. I'm doing 54 over 3x, take away 2x squared over 3x. I'm splitting up the fraction. Then I can simplify this first one to be 18 over x, because 54 divided by 3 is 18. Then 2 over 3, that's 2/3. Then x squared divided by x is just x. And I'm going to say that's y. Right? Now I can then substitute that into my volume. So sub y into my volume, which was v, is x squared y. So then my volume is going to be x squared times my y of 18 over x. So okay, 2/3 x. And I'm in a good position now because I've just got x's on its own. Okay, so that I'm going to hopefully lead to my answer. So then my volume, x squared times 18 over x, that'd be 18x. Then minus 2/3 x times x squared would be minus 2/3 x cubed. Right? And that's my volume. And hopefully that matches the answer. Right? Yes, 18 minus 2/3 x cubed. Cool. Okay, part A. There we are, we got there. So that is my expression they wanted. Cool. Now, for part B, they want, we're now told that given x can vary, we usually take that for granted, but all that means is we can, because x can vary, it basically makes it a function, right? Because if you think about a function, like a normal function graph, like x always changes, right? In this case, x can change here, so we can differentiate. Anyway, so x can vary. We can now use differentiation to find the maximum or the minimum value of v. Well, to find the minimum and the maximum using differentiation, well, let's differentiate it, right? So then dv dx, if we differentiate this with differentiate v with respect to x, this expression here, well, 18x will go to 18. Then minus 2/3 x cubed, that should be an x cubed there, my apologies. But minus 2/3 times 3 would be minus 2x, then it'd be squared, right? Because we knocked one off the power. Right, okay, that's my expression, that's my derivative. But now it's asking to find the maximum or minimum value. That's going to be to do with the maximum or the minimum point, which are stationary points, and we know that means dv dx and the derivative has to equal 0. So now we just solve that, right? So 18 minus 2x squared will equal 0. So then that means 2x squared equals 18. So therefore x then, well, x squared would be 9 because 18 divided by 2 is 9. So root 9, it'd be plus or minus 3. Okay, so x is plus or minus 3 there. Right, okay, so I've got two possible values. X is plus or minus 3. Let's have let's kind of, which values can we take? Well, think about it, x is a length, right? That means x cannot be negative 3. It has to be positive. So x is a length. So that means the only value of x we can take is positive 3. As x is positive, okay? So x cannot be negative 3. So there we are. So x is 3, and so then that x then will give me the maximum or minimum value because it's a stationary point, right? It gives me it'll be a maximum or a minimum in this case. So then to find the maximum or the minimum value of my volume, then remember that it wants the maximum minimum value of the volume. Well, we need to substitute x back into my volume, right? So remember volume v, remember from part A, was 18x minus 2/3 x cubed. So then if x is 3, then v, if I substitute that in, it's going to be 18 lots of 3 minus 2/3 lots of 3 cubed. That would get me 36, and that would be in centimeters cubed, I think. Meters, my apologies, meters cubed. Okay. So that would then be my maximum or minimum volume, right? Because it's based on the maximum or minimum point x here. So there we are. So that is the maximum or minimum. I don't know which one it is, but that is a maximum min value of v because it's the maximum min stationary point here. Okay, part C. Now you might be thinking, because of that, well, which is it? Is it going to be a maximum or a minimum? Which is it? Or none at all? Which is it going to be? This is where part C comes in. Justify that the value of v you found is actually a maximum. How are we going to prove it's a maximum then? Well, if you think back to when we looked at stationary points, we can use the second derivative, right? So remember the second derivative, so d squared v here with respect to x, so dx squared. If it's a maximum, it has to be less than 0. If x is a maximum. Okay, remember that's the second derivative test. And likewise, if it was greater than 0, if it was positive at x, then it'd be a minimum. But this case, it has to be less than 0, and then it's a maximum. So we need to check the sign of the second derivative. Well, we don't have the second derivative, but we can get there because we know what the first derivative is. It's this expression here. dv dx is 18 minus 2x squared. So if I write that down here, okay. So then that's my first derivative. So my second derivative, I need to differentiate this, right? So then that would be where 18 goes to 0. Then minus 2x squared will go to minus 4x. Then I need to check I need to check that well, x is 3. That point is a maximum, right? So at x is equal to 3. My second derivative is going to equal minus 4 lots of 3, which is minus 12. Well, what do you know? That's negative. Great news. That means it has to be a maximum then. So as d squared v dx squared is less than 0, x equals 3 must be a maximum. And there we are. Cool. Yes, so that is basically how a lot of these questions work, right? And I should say part A can be quite challenging, right? Quite a lot of stuff to consider, but please don't be thrown off because they give you the answer to part A. You can use part A to then do part B and C. And hopefully you saw with part B and C, it's basically just differentiation, right? That we looked at before. So don't be put off by the whole question if you can't do part A, okay? If you don't know how to get that expression, that's okay. Just work with that. They give you it. Then you just differentiate that in the other question. And then you pick up the marks, okay? But that's the idea. You'll find with a lot of these questions, especially the exam questions, which we'll be looking at now in a moment, it works in the same sort of way where we need to consider the volume and the surface area and kind of like do simultaneous equations, substitute one into the other. Then we get the equation, then we can differentiate to get a maximum and minimum. Then we differentiate again to get the second derivative to prove it's a maximum minimum. That's how a lot of these questions will work, okay? Right, so we're going to look at some exam questions then. Okay, so we got this exam question then. We are told a lorry is driven between London and Newcastle. In a simple model, the cost of the journey when the lorry is driven at a steady speed of v kilometers per hour is this equation here. So that's basically saying that it tells me what the cost will be of the journey at a particular speed v, okay, and I can just substitute that in, right? So I am asked to find, according to the model, the value of v that minimises the cost of the journey. minimizes, so it should be alarm bells that you should be differentiating and setting to 0, right, to get a minimum point. So that's going to be, well, it won't be dv, so it'd be the variable c with respect to v, right? That would have to equal 0, right? But in order to do that, I need to know what dc dv is, right? So I know that c is, again, 1500 over v, add 2v over 11, add 60. So I need to differentiate v. I need to differentiate the v variable, right? So I need to do dc dv. So differentiate the v variable in my equation here. But I can't do that at the moment because I've got this fraction over v. I need to write it as a power, right? I can't have anything over v. So to do that, I can just do 1500v to the minus 1 as it's a reciprocal. Then we add 2 over 11 lots of v, add 60. Now we can differentiate. Okay. So now, if that is equal to c, then dc, the derivative with what we say respect to v, the variable v, if we differentiate with the variable v, well, firstly, 1500v to the minus 1 would be negative 1500v to the minus 2. Add 2 over 11, and then the 60 goes to 0, and that's it. So that's my derivative, but then we want to find the minimum, so we need to set it to 0 to give that stationary point to that minimum point. So minus 1500v minus 2, add 2 over 11 equals 0. Right, so now I need to solve for v to find that point v. Okay, but in order for me to help see what I need to do, let's probably best to convert this v minus 2 as a fraction, right? So therefore, minus 1500 over v squared, add 2 over 11 equals 0. Then I could just times everything by v squared, both sides. So then minus 1500, add 2 over 11 v squared equals 0. Then I can do 2 over 11 v squared equals positive 1500. Then I can then divide by I can divide by 2 over 11 to both sides. So then v squared can equal 1500 divided by 2 over 11, which should get me 8,250. That's v squared. So therefore v is going to be the root of that, right? Plus or minus root of 8,250, which will get me at 5 root 330 simplified in my calculator. Okay, but again, plus or minus, you'd probably be plus, right? It can only be positive. Yes, because it's a speed, right? Speed. Think about it. If you're driving, you can't really do negative kilometers per hour or miles per hour, right? V has to be positive. Okay. As v is a speed, v must be positive. So v equals 5 root 330 kilometers per hour. So kilometers per hour there. So that's the value of v. Then it says to find the minimum cost of the journey. So we found the minimum value of v. So then the minimum cost, which is c, I need to plug that v into my formula here to get the minimum c value. Right, so that's what we're going to do. So as v, I'm going to substitute v equals 5 root 330 into the formula c equals, what was it? 1500 over v, add 2 over 11 v, add 30, was it? 60, okay. So then if I do that, then therefore c is going to be 1500 over v, which should be 5 root 330. Add 2 over 11 lots of 5 root 330. add 60. Then if I put that in the calculator, I will get probably best to give that as a decimal at 93.03 to 2 decimal and that being pounds, right, to 2 decimal places. Yes, because cost, also you always pay attention to units in these sort of questions. It's in pounds, right? I'll even mark it pounds v kilometers per hour, which is kmh minus 1. Always underline your units with these sort of questions, right? Then they might be worth a mark for writing your units. Okay, so that's my minimum cost then, right? That's my minimum cost. There we are. Because that's my minimum. Was it maximum cost or minimum? Well, I assume it's the minimum because it's the only stationary point. But part B then says we need to prove its minimum. Okay, so now we're going to prove that is the minimum value. We need to use again that second derivative. We need to use d squared, the second derivative, d squared c, d squared v. So we know that the first derivative, again, the first derivative, which we did in the previously, where was it? It was here. Minus 1500 v minus 2. Add 2 over 11. Was that right? Yes. So that's my first derivative. Then I need to consider the second derivative. So I need to differentiate again. So if I differentiate that expression again with respect to v, right? So that would be v to the minus. So that would be plus 3000 then, because minus 1500 times minus 2, my power comes to the front, times that by minus 2, I get positive 3000, v to the minus 3, as I subtract 1 from the power, and then the 2 over 11 goes away. So then I'm going to say I need to substitute my minimum v point here, right? 5 root 330, 330. At v equals 5 root 330. If you want to show that this is the minimum, then we need to consider the sign of the second derivative. So then if we substitute that into my second derivative, that'd be 3000 lots of 5 root 330 minus 3. If I put that in the calculator, I would get .0.004 blah blah blah. That's positive, right? And that's great news, because we know, well, we should know that that because the second derivative here is positive, that means that v, my point b, is a minimum. It indeed must be a minimum. Must be a minimum. Okay, and that's because, again, if it's positive, the second derivative, it will give me my minimum. Okay, and that's great news, really, because if you think about it, we want that minimizes the cost. That gives me the minimum value of the cost, which makes sense, right? Because we want to make it as least costly and as cheap as possible, right? So again, it feeds into the idea of optimization, of lowering costs as much as we can, and this is where differentiation helps. Okay, so that's really it. Then the last part of the question, state one limitation of the model. You get these questions, these rubbish questions, with these sort of modelling ones occasionally. So you really got to think about what maybe doesn't make sense. Read carefully what they say. So in a simple model, the cost of the journey is driven at a steady speed. that means the speed is constant throughout. So imagine, so for example, when v was 5 root 330, as a that would be as a decimal 90.8 kilometers per hour. It's kind of alluding at the fact it's kind of going to be at roughly the same speed all throughout the journey. Does that make sense? Not really, because if you think about it, it's going to be traffic. Are you really going to be travelling at the same miles per hour, for instance, all the way throughout a journey? No, because there'll be traffic jams, you'll be slowing down, all the stuff like that. So that is a limitation. So the limitation is, in reality, a lorry would not be driving at a steady speed, e.g. because of traffic, right? That will slow you down and bring you to a halt, right? And yet you could also probably say as well, this, if you look at the equation, well, what happens if v is 0, right? When the lorry's not moving, it wouldn't have any cost. So you'd expect c to equal 0 because there's no cost when it's not moving. But actually, it's not even defined. The model doesn't actually define it, because we'd be dividing by 0 because we're dividing by v. So that would be another flaw as well, that or model not defined when v is equal to 0. As cost should be 0, right? So you could use either rule, but you kind of just gotta, when you do more of these modelling questions, you will start to pick up the sort of ideas that you can that they kind of look for, the sort of limitations, what maybe isn't so realistic in real life, the things that could impact in real life that would affect your answer, stuff like that, right? But that's kind of what they're going to be looking at. Okay, so that's the rough idea. Cool. Okay, so we got this question now, which is kind of reminiscent to one of the earlier examples. So we're told a company makes drinks containers out of metal. The containers are modelled as closed cylinders with base radius r and height h, and the capacity, which is volume basically, is 355 centimeters cubed. Hence its volume, right? Because it's centimeters cubed. The metal uses for the circular base and the curved side, that cost 0.04 pence per centimetre squared. So it's talking about the surface area. And the circular top costs 0.09 pence per centimetre squared. Have negligible thickness. Show that the total cost to cover the container is this. Right, so a lot of stuff going on here. Let's kind of, I guess, sort of break it down. So firstly, it's talking about cylinders. Again, I can sort of sketch maybe what one might look like. So if I draw like a rough cylinder, right? Oh, that's horrible. Something vaguely like that then. And we know a cylinder will have a height of h and a radius r. Okay, okay, so that's what's going on. And we're also told then that the volume, the capacity, is 355 centimeters cubed, right? So, that's the volume. Now, this bit is talking about the surface area, because it said the circular base, which is this shape down here, the base here, which is a circle. Doesn't look like one, but believe me, it is a circle. The circular base and the curved side, which is basically this, right? The curved side, the area of those faces costs 0.04 pence per centimetre squared. So every surface area costs 0.04 pence. Then the circular top up here costs 0.09 pence per centimetre squared. So we need to consider the surface area, right? The surface area. Okay, so my surface area then, well, firstly, we got the base here, right? We got the base, and that's a circle, right? It's a circular base, as again, a cylinder, the base, and the top is a circle. So firstly, the surface area, again, is the area of sort of the 2D parts. So this 2D circle at the bottom, the surface area, the area of that, well, firstly, it's a circle, so it's going to be pi r squared, and that's the area of that circle. Then we have this curved sort of main side, right, exposed. That's the curved side. The surface area of that then, well, you could remember it as, well, you should remember, because again, we're not given the formula for cylinders. You do need to remember it, unfortunately. But the surface area, the area of the curved side here, that is 2 pi RH. I remember that because of the idea that really a cylinder is just a bunch of circles stacked upon each other, right, with the same radius, right? So then all these circles, the same circles with the same radius, although obviously my sketch is a bit bad, but they're all the same circles, all stacked upon each other up to a height of h. So then if you imagine the surface area of the surface area of the side here, it's the outside, it's the circumference of all the circles combined, right? Well, the circumference of one circle, that's just 2 pi r. Well, that's no coincidence here. We got 2 pi r. That's the circumference of one circle. So the total circumference, the total outside the edges, right? That gives me the surface area. We then multiply by h, because then that's how high up we are, right? So that's how we can get the curved surface area, as the curved bit is just all the circumferences of all the circles added together, right? So it's 2 pi RH. But either way, you do need to remember it, unfortunately. Then lastly, obviously we've got the top, which is also the same circle. So that's also pi r squared. So that's my total surface area. Okay, but they're not really asking for the surface area, they're asking for the cost of the surface area. It's talking about the cost of all the surfaces, okay? Well, firstly, the circular base has a cost of 0.04 pence. So cost of base, which is going to be, again, this side down here, but the surface area is pi r squared, that's the area, but we're told here, again, per area, it's 0.04 pence. So the total cost is 0.04 times my area, pi r squared, right? And so that would be 0.04 pi r squared, okay? Then we're told to find we're told also the cost of the side, the curved side, is also 0.04 pence per centimetre squared. So then the cost of the curved side, the surface area is 2 pi RH, right? That's the surface area of this whole curved main side here. Then the cost then is 0.04 pence per centimetre squared. So the total cost is my surface area times 0.04 again. That'll be 0.08 pi RH, right? And then lastly, I need to find the cost of the top face here, the top circle. We're told in this case the circular top costs 0.09 pence per centimetre squared. So the total cost of the top then, well, the top again has an area of pi r squared, but then the cost per area is 0.09. So we times that by 0.09 to get the total area, the total cost of the area of 0.09 pi r squared. And there we are. So then we can add. Them all together to get the total cost of the whole shape, the total cost of the whole area by adding all these three individual areas together to get 0.04 pi r squared, add 0.08 pi rh, add 0.09 pi r squared. Then I can add the pi r squareds to get 0.13 pi r squared, add 0.08 pi rh. So that's my cost then, right? So that, but I need to match the equation I've given, the cost there. What do I notice? There's no h involved, right? There's no h. I have a h here though, I need to get rid of that. How can I get rid of h? Well, I'm given the volume, right? Well, I also should know that the volume of a cylinder is pi r squared h. Because again, it's no coincidence that firstly the pi r squared bit is the area of one circle. So then I'm multiplying it by h, right? So by how high up I am. So that gives me the volume, the space inside. So I'm given that the volume is 355, right? So then I can sort of equate that to then say that pi r squared is 355. So then I'm going to get rid of h. So if I rearrange for h, it's going to be 355 divided by pi r squared, right? Then I can substitute that into my cost, right? My cost C. So C is going to be 0.13 pi r squared at 0.08 lots of pi r of h, which I can then substitute h in. So 355 divided by pi r squared. Okay, so then I can multiply the top right. So then C is 0.13 pi r squared at 0.08 times 355. That would give me 28.4 pi r divided by pi r squared, right? So I've just expanded the fraction, so I times the top number, so 0.08 times 355 gets me to 28.4, right? Then I can then simplify this because pi and pi cancel and r, the radius, cancels with the r squared on the bottom, and I'm left with C to be 0.13 pi r squared add 28.4 divided by r, okay? Because remember, r over r squared gets me 1 over r, okay? So I'm left with the radius at the bottom there. Well, actually, then if you match what they wanted, that's exactly what they wanted now. So there we are, we've got the formula. Cool. Okay, I think that's a very tricky question there. Hopefully you sort of understood what I did there. The idea is essentially, we worked out the surface area and the volume of a cylinder, which again you do need to know, unfortunately. But there's this added complexity about cost as well. The cost of each surface area as well. So I have to multiply my surface area by the costing as well, okay, of each side. Right, okay. So that's part A. Then part B, now that we've got the formula, we need to use calculus. We'll talk more about that in the next section when we look at integration, but calculus can just mean differentiation, right? So a fancy word for, I guess, differentiation and integration, but for now we look at differentiation. Use differentiation to find the value of r for which C is a minimum. So again, it's this idea about finding the minimum point, the minimum r value, the minimum value for r, right? So it's to do with stationary points and minimum points again, right? So we need to differentiate, right? So again, if C is equal to this expression, well, before I differentiate, right, I need to get this R as a fraction. I need to get that as a power of R, right? Not as a fraction, but as a power. So then I can say 0.13 pi r squared and 28.4 r to the minus 1. Then I can differentiate to then get 0.13 pi r squared. If I differentiate the r, the squared, the power, will come to the top. Multiply 0.13 by 2, I get 0.26 pi r. Okay. Then 28.4 r to the minus 1, the minus comes in front, so it'll be minus 28.4 r minus 2. And that's my derivative. Then, okay, so now I want to find the minimum. That has to be a stationary point, which has to be set to 0. So that means I need to set this equal to 0. And I need to solve for the r. Okay, so again, I should convert this index back as an actual fraction to make it easier to solve. All over r squared equals 0. Okay, now I can multiply everything by r squared, everything in the equation, to get rid of the fraction. So then 0.26 pi r cubed, r times r squared is r cubed, minus 28.4 equals 0. Then I can solve for r, so then 0.26 pi r cubed equals 28.4. So then I just divide by 0.26 pi to get r cubed is 28.4 over 0.26 pi. I don't think that would have been quite nice, so I wouldn't imagine. So 28.4 divided by 0.26 pi. Yeah, we get a nasty decimal. Okay, so I'm going to leave it as there. So then what I get then is r cubed is 34.769 blah blah blah. So I need to cube root that. So then if I cube root that, I get r to be 3.26 centimeters, is it? Let's say 2 decimal places when I round it. Okay. So that is my minimum r. Well, not my minimum r value, but it will give me the minimum. Okay, that value of r will give me the minimum then, right? So then I need to find the minimum cost. I need to find the minimum c. So I need to substitute that r value into my c, my formula to find c. Okay. Well, as I remind you, c is this expression here. For c is 0. So I'm going to substitute this r into c, which is equal to 0.13 pi r squared, add 28.4 over r to the minus 2, right? R to the minus 1, okay. Okay, so I'm going to substitute that r then. That r, which is this 3.26, into this expression. So therefore c is going to be 0.13 pi of 3.26 all squared, add 28.4 times 3.26 to the minus 1. Okay, if I put that in a calculator, then I'm going to get 13.05 to do decimal places, and the units are in pence. Okay, in pence. It doesn't say to round it to anything, does it? Oh, to 3 significant figures. Oh, okay. So to 3 significant figures, that'd be 13.1. Okay. And there we are. Okay, cool. So that's the minimum value of C, my cost. Okay. Then part D. Oh no, sorry. Part C says, using the second derivative, prove that the cost is minimized. So we need to prove it's minimized. Okay. Well, we need to again use the sign, the second derivative test, look at the sign of the second derivative at the value of r, okay? Well, if we're going to do that, I need to find the second derivative, right? So if I remind you, the first derivative, which we calculated, was this expression here, 0.26 pi r, take away 28.4 r to the minus 2. So then if I differentiate that again to get the second derivative, I'm going to get 0.26 pi, right, because the r will go away to 1. Then minus 28.4 r to the minus 2. The minus 2 comes to the front. So I'll do minus 28.4 times minus 2. That will be positive 56.8 r to the minus 3 when we knock 1 off the power there. Okay, so then at the value of r then, which was 3.26, which we calculated, 3.26, the second derivative will be 0.26 pi add 56.8 lots of 3.26 to the minus 3. If I put that in the calculator, I will get 2.46, right? And that will be that's to say 2 decimal places. That is clearly then greater than 0, right? It's positive. So that means therefore, since the second derivative is positive, that has to mean it's a minimum. Then r, which is 3.26, is a minimum. And so there we are, the cost is minimized, and that's what we've proven. Okay, part D then, it says hence find the minimum value of C. Okay, giving it to the nearest integer. Oh, that's interesting. Well, we already worked out the minimum value in part B, so I guess if it's to the nearest integer, we just round it, I imagine. Don't know. Okay, so I guess we just round my answer to part B. So part D. So okay, the minimum value of C is equal to, from part B, that's what we worked out, was 13.1 pence, right? To 3 significant figures, right? From part B. So then to the nearest integer, that would just be 13p. And there we are. Okay, that's it then, I guess. Done. I don't know. So it's just to the nearest integer. That's that then. Okay. Oh no. That's why. I did part D already. No, part B. I didn't read the question. I did more than I needed to. For part B, I only needed to find the value of R. For part D, I needed to find the minimum value of C. Okay. I did that already. Okay. So there we are. There we are. Okay. Yes, my R is already to 3 significant figures. Okay, that's all cool. Okay, there we are. Okay, so this would have been part D then. Okay, that would have been part D. If I rounded that'd be 13p to the nearest whole number, to nearest integer. Okay, I just got I just did a bit more work in the earlier parts of the question, but that should be fine. Okay, so that's my part D there. Okay, so once I found the value of R, I then substituted that into the equation to find the C, the minimum value of C. Okay, and there we are. Okay, so again, very similar sort of format to the earlier example, and again, my advice is part A is very tricky, right? Very tricky. You are given the formula though, so if you can't do part A, you can still access 8 marks, right? There's a lot of marks, and that is just differentiation, right? That should be a bit more accessible and easier to do than the than part A. So if you can't do part A, do not worry and just skip the whole question. Please try and do the other parts, which are just differentiating that expression, okay? But hopefully that made some sort of sense. That's the core idea, right? That usually we want to consider the volume and the surface area of the shape, okay? And then just kind of substitute one equation into the other to get the expression they want, okay? Okay, we're going to finish off with one more question, which is, again, very similar, but I do want to practice it, though. This exam question here. And this time it isn't a cylinder, but that's fine. We're given the formula. I know it is a cylinder, but it's also a sphere. But we give them the sphere anyway. Anyway, so we're told a manufacturer produces a storage tank, which looks like this. The tank is modelled in the shape of a hollow circular cylinder here, closed at one end with a the hemisphere here, which is half of a sphere, a half a sphere. Shell at the other end, right? And they've drawn it for us. The walls are assumed to be negligible thickness. The cylinder has radius r and height h meters, and the hemisphere has radius r. They've drawn all that on the diagram as well. The volume of the tank is 6. Okay. So immediately I'm going to note that the volume is 6 meters cubed. And again, a very sort of typical question here. We need to show that the surface area of the tank is this expression here. So that's what we're going to consider then. So the volume is 6 meters cubed, but it's asking for the surface area. I'm going to do the surface area down here then. Well, what is the surface area going to be of this tank here, this shape of the cylinder and the sphere joined on top? Okay, so obviously it's all the faces that are exposed, right? That are facing outside the shape. So firstly, again, it's this circle base at the bottom. What's that going to be? Pi r squared, right? The area of the base circle is pi r squared there, right? So I can do pi r squared. That's my base. Then the curved cylinder face here, the curved, is going to be 2 pi r h, right? The circumference times by h. There we are. Okay, then it's the sphere. It's the surface area of the sphere, or the hemisphere, technically. Well, the hemisphere again is half of a sphere, right? And hopefully you can see that, right? Half of a sphere. And you can see that there because half of it's been chopped off, right? The sphere on the top. So that means it's going to be half of the surface area of a sphere. Well, what is the surface area of a sphere? We're told it here. You don't have to remember that, but you do need to remember the cylinder. But the sphere surface area is 4 pi r squared. So the hemisphere is going to be half of that, half of the sphere, right? So that's going to be well, half of 4 pi r squared is going to be 2 pi r squared, right? So I can just add that on. But then actually I can collect this pi r squared terms to be 3 pi r squared, add 2 pi r h. And there we are. That's my surface area. Okay. But does that look, is that the formula they want? Is that the surface area? No. Why is that not the case? Because we have a h. There's no h in their final answer, but in my answer at the moment I have a h. I need to get rid of the h then, right? But this is where the volume's going to kick in. I need to find the volume of it because I'm given the volume. So what would the volume be, right? In general, the volume of this shape, well, it's going to be the volume of the sphere, of the cylinder part, and then the volume of the hemisphere. But the volume of the cylinder is going to be pi r squared h, so the area of the circle times by h. And then this hemisphere, again, because it's half of a sphere, the volume has to be halved. But the volume is 4/3 pi r cubed of a sphere, so half of that is going to be 4/6. So 4/3 divided by 2, 4/6 pi r cubed. Well, that simplifies to 2/3 actually. And there we are. So that's my volume then. I now need to equate that to 6, right? So therefore pi r squared h, add 2/3 pi r cubed is going to equal 6. And now I need to rearrange for h if we're going to substitute h into the surface area. So pi r squared h is going to be 6 take away 2/3 pi r cubed. Then I can then divide by pi r squared to get h is 6 minus 2/3 pi r cubed all over pi r squared. Okay, I can now simplify this. I can split up the fraction. So then I'm going to get 6 over pi r squared minus 2/3 pi r cubed all over pi r squared. And I can simplify this fraction here. Right, that will go to 6 over pi r squared. Then the pi's cancel and the r's cancel too. R squared, r cubed. I'm left with 1 r on the top, right? So that'd be minus 2/3 r. And there we are. So now that is h. I can substitute that into my surface area to then get that to be 3 pi r squared. Add 2 pi r lots of h, which is now 6 over pi r squared minus 2/3 r, right? And now I just expand this, so that'd be 3 pi r squared, add 2 pi r times 6, that'd be 12, right? 12 pi r divided by pi r squared minus 2 times 2 is 4 pi r. And r times r is r squared over 3, okay? So 2/3 r times 2 pi r is 4 pi r squared over 3. Then I can simplify these fractions. So 3 pi r squared, then the pi r and the pi r down here cancel to be left with 12 over r. And then minus 4/3 pi r squared, okay? Right. Okay, how am I looking? Okay, I can actually I notice I have 2 pi r squared terms here and here. I can then collect them together. So if I do 3 minus 4/3, so 3 so what I have is 3 pi r squared minus 4/3 pi r squared, add 12 over r. I can add these first two terms together. So 3 pi minus 4/3 pi is 5/3 pi r squared plus 12 over r. How does that compare? Yes, cool, that is the formula we want. It's 12 over r, add 5/3, 5 over 3 pi r squared. And that's what we got. Cool, okay, cool. Again, that's probably the hardest part of the question. Again, if you're a bit stuck on that, please just try to do the other parts of the question, which we'll do now. It's just a bit of differentiation. Now, we're told the manufacturer needs to minimise the surface area. We need to minimise this expression here. And it's asking us to find the radius for when it's a minimum. So we need to find the minimum radius point, if you will. So that's going to do with differentiation, right? So if I call that S then for surface area, then I want to differentiate S, my surface area, differentiate that with respect to R, so differentiate the R variable. If I do that, well, so R squared, the 2, obviously the power comes to the front, so 5/3 times 2 is 10/3 pi R, as I subtract 1 from the power. Then 12 over R, well actually, that needs to go to 12r to the minus 1, right? As a power. Then I can differentiate that to minus 12r to the minus 2. Then, again, if I want to find the minimum, it's going to be a stationary point. I need it to set it to 0. So, that means this expression, 10/3 pi r, take away 12r to the minus 2 equals 0. And I need to solve for r. Well, again, to help me, let's convert this power back as a fraction. So 10/3 pi r, take away 12 over r squared equals 0. Then again, I can times by r squared to all the terms. to get rid of the fraction to both sides. So then 10 thirds pi r cubed, take away 12 equals 0. Then I want to solve for r. So then 10 thirds pi r cubed equals 12. So therefore r cubed is going to be 12 divided by 10 thirds pi. If I put that in the calculator, that gets me it gets me some decimals, so it gets me 1.1459 blah blah blah. So then if I cube root that, I then get r to be 1.046 blah 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 centimeters, I think. Meters, okay, meters. It doesn't say to round it to anything, so I'll just leave it as that then. 1.046 centimeters to let's say 3 decimal places. And there we are. Okay, cool. So that's the value of r. That would minimize it then. So that's part B. Then part C, again, you probably guess what's going to come up. We need to prove. I thought it was going to say find the second derivative. Okay, we don't need to do that. I guess the question trust that it is a minimum. We can prove it's a minimum by checking the second derivative, but it's asking us to then calculate the minimum surface area. Okay, we don't need to check it's a minimum. It just says to calculate the minimum surface area. So what we're going to do then, with our value of r that we found, we're only going to plug that into my surface area, right? Into here. So if I remind, I'm going to substitute r into my surface area, S, which is 5 thirds pi r squared. Add 12r to the minus 1. If I then plug my value of r, which is 1.046 into here, that'd be 5 thirds of pi of 1.046 squared. Add 12 lots of 1.046 to the minus 1. Okay. Then if I put that in a calculator, I will get 17.2. That would be in meters squared because it's an area, right, in meters. And then if I was to round it to the nearest integer, that'd be 17. And there we are. And that's the question done. So those are the those are questions I've had then. So hopefully you get a sort of good idea now of how we can sort of approach these questions. Hopefully they're kind of similar, but the idea is we can find equations, find the volume and the surface area, or whatever else. Maybe they might even just give you the formula, like in this question. Where was it? This question here, right? This question they just gave me the formula, but sometimes we might have defined it using the surface and the volume. Once we've got to that point, then we can just differentiate, define the minimum or the maximum value, and perhaps even differentiate again to prove that's a minimum or maximum by checking the sign of the second derivative. But hopefully you sort of got an idea now how to tackle these modelling questions. But yeah, that's it for differentiation for year 1. But I'll see you next time.